I like to tell my first year students that good physics should have beauty and simplicity. We treat one-dimensional problems mostly in first year physics classes because of their inherent simplicity and resulting beauty. When we treat two-dimensional and three-dimensional problems, the analysis gets more complicated and sometimes the beauty suffers as a result of that, but we can restore the beauty by proper analysis and proper data taking techniques. One of the aspects of the Sphero Mini sensor board project that we have yet to implement is to recognize that the sensor board has a three-dimensional gyro. It measures roll, pitch, and yaw angles, the angular velocity in roll, pitch, and yaw. When we roll the sensor board down a hill, we align the yaw axis, gyroscope axis, with the axis of rotation of the cylinder. But today I want to show you what is possible, at least in a qualitative way, to use all three dimensions for the gyroscope. When my wife and I put the kits together, inside the top and bottom shell of the sensor board, Sphero Mini, we put foam rubber inserts that will hold the sensor board in a plane that is parallel to this axis of the sensor board. So that as you roll down an arbitrary surface and the roll becomes three-dimensional, you can measure all three axes of rotation. So let's roll this down the surface of a cone. So now you see the gyroscope data, pitch, roll, and yaw. The green is pitch, the purple is the roll, and the yellow is the yaw. The rapid variation you see is the rotation. There are three time scales. The rapid rotation gives you the fastest variation here, the quick wiggles up and down. Then over a longer period of time, the three degrees of freedom gyroscope readings change phase relationship to each other. First mostly yaw, mostly roll, mostly pitch. Then they become random, and by the time it's gone very far, it looks like a total mishmash of data. Slowing down, notice that the vertical time scale is auto-scaled, so the variation is getting less and less, and now it's pretty much come to a stop. Before we analyze this three-dimensional data, let me go back to the one-dimensional case, the case of the cylinder rolling down a ramp, and remind you what we did there. We looked at a cylinder starting from initial height h above the datum point. At the top, the potential plus kinetic energy is just potential energy, mgh, and that at the bottom, as the cylinder rolls without slipping, that potential energy, mgh, gets converted to 1/2 mv squared translational energy and 1/2 I omega squared rotational energy. The moment of inertia here of a cylinder is this, and rolling without slipping tells us that the velocity translation in the omega, the rotational velocity, are related by v equals r omega. So to do the three-dimensional analysis, then all we have to do is replace the moment of inertia with that of a solid sphere. And the omega now, which was a one-dimensional scalar, one-dimensional angular velocity, now the vector velocity omega has three components: a roll velocity, a pitch velocity, and a yaw velocity. The total energy, kinetic energy, then k½ is 1/2 I omega squared, but now omega squared is the square root of the sum of the squares of omega squared roll, omega squared pitch, and omega squared yaw. So here is the raw data from the Sphero sensor board, again for the pitch, roll, and yaw. Those three components in it, random phase relationships. Here now is the square root of the sum of the squares, and you see this random phase components of the omega add up in a vector sense to a very smooth curve down here, and you see the general decay of the kinetic energy as the ball rolls down the cone. So this is not a complete experiment. It's an invitation for the community to start looking at three-dimensional issues. And I'm simply drawing your attention to the fact that it's very easy to get omega squared total from the three components of the angular velocity.